This is probably the most complicated video in the series about stirred tanks. I'm going to involve almost every component that will be factored into our analysis of stirred tanks. So let me draw what I'm talking about. So we have a stirred tank, we have input and output streams. I'm going to put a chemical reaction. So we have a liquid level L, a chemical reaction A goes to B. I'm not going to make it reversible, so it's just an irreversible forward reaction. We have CA as a function of time, CB as a function of time. The input stream has A only at a concentration CA in. F in is the flow rate in. I'm going to say it can be a function of time, but I'm not actually going to treat it like a dependent variable. I'm just going to imagine that the operator of the reactor can control a valve and control F in at will. So it's not something that's going to depend on the other variables, but it could change in time. So F out, again, another thing that could change in time. CA at time t and CB at time t, these are going to equal the concentrations in the tank, and those are dependent variables. So we're going to make additional assumptions. So A sub C is a constant cross-sectional area. There is a delta H reaction, and that, so there's a heat of reaction that's constant, and also the rate constant follows the Arrhenius equation, K0E to the minus EA over RT. And fluid density rho is constant. Okay, so when I ask questions on exams about formulating differential equations, usually the phrasing I use is, I'd like you to formulate the system of differential equations that will be needed, or that will need to be solved or could be solved in order to calculate something. So in this case, let's say CA as a function of time and CB as a function of time. And I expect students to recognize or be able to analyze how many equations need to be formulated. So I'll discuss that a little bit. So first of all, if we're concentrating on component A, let's start with a balance on component A. So let's do a balance on A. And we do our usual balance equation. Accumulation equals in minus out plus generation minus consumption. Okay, so the amount of A in the tank at any given time is going to be the concentration of A times the volume of fluid. So in this case, LAC. And if we're talking about accumulation, we're going to define this at some time t plus delta t. We're looking at accumulation over some small interval of time, delta t. So we take the same quantity. Let me fix that L. And we evaluate the same quantity at time t. So accumulation is going to be how much more A is there at time t plus delta t versus time t. And here are the reasons why it would change. One reason why it would change is because we have A flowing into the system. Our control volume is the tank itself. So A flows into the system through the input stream. So let's see how much flows in at a time step delta t. So it'd be Fn Ca in delta t. Likewise, A flows out. F out Ca delta t. And so we could have generation, but notice that this is an irreversible reaction. So the chemical reaction does not generate, but it does consume A. So let's write out K naught e to the minus EA over RT, the rate constant K times CA L AC delta T. Okay, I want to make it clear that the kinetics could be written as KCA, but the reason I write this out is because I want to make it very clear that K is not a constant. It depends on temperature. So we'll discuss that a bit more in a few minutes, but let's actually work through this equation. So I'm going to factor out AC because that's a constant. L is not a constant. You got to be careful about that because in general, if F in and F out are not the same, the fluid level in the tank can go up and down. So L is time dependent, so is CA, but AC is not. We assume AC is a constant. So I'm going to factor that out. So I'm going to say AC times CAL at T plus delta T minus CAL at time T. Well, I should put parentheses here. I'll put brackets around that to make it clear. I'm also going to divide through by delta T. This is going to equal F in CA in minus F out CA minus K naught e to the minus EA over RT CA and LAC. Okay, so now the next step is going to be to take the limit. So I'm going to take the limit as delta T goes to 0. So what this is going to then become is AC d by dt of CAL, and this is going to equal F in, I guess I can just copy all this. Okay, let me make that look a little better. Okay, so this is a differential equation that describes CA as a function of T. Now, I did not say this is a differential equation that we can solve because we actually can't solve this. I know we haven't discussed methods of solving, but the problem here is that there's not just one variable that depends on time. So CA depends on time, but so does L, and so does temperature. And so we actually would need additional equations. So this is the sort of thing I expect my students to be able to see. We would need separate equations for L and also temperature. So let's actually work out the balances. I'm going to leave a little room here because I'm going to simplify. Once I actually have an equation for L, I can actually simplify this a little bit. But initially, I tell students not to worry so much about simplifying the equations or putting them into any specific type of form, but rather just formulating the equations is a good place to start. So let's actually do a balance on fluid. And implied here is that we're actually doing a mass balance. Let me copy the picture just so you can see it while we work with the equations. Okay, so what we're really balancing here is overall mass. We're treating A as if it's a solute, A and B as if they're solutes. And we're treating the system as if the solvent fluid density dictates the density of the whole solution and that it's not going to change over the course of the process. So the mass input, actually let's write our usual accumulation equals in minus out plus generation minus consumption. Mass is not generated or consumed in this system. Accumulation refers to how much mass is in the tank and how much that changes over the interval t to t plus delta t. So let's say this is the mass in the fluid is going to be density times the fluid volume, LAC, at t plus delta t minus rho LAC at time t. And the input is going to be rho F in delta t. The output is going to be rho F out delta t. Now, since the density is constant and it appears in every term, we can actually cancel it. What that effectively means is that when fluid density is constant, you can conserve, you can treat volume of fluid as if it's conserved. So that's a common thing to do. And also notice that AC is a constant, so we can factor that out. So I can say AC times L at t plus delta t minus L at time t. I'm going to divide through by delta t. And just like before, I always do this in differential balances. I'm going to take the limit as delta t goes to 0. And on the other side, I'm going to have F in minus F out. And this becomes dL dt. So what the equation is, we can write as dL dt. We don't have to do this, I guess, because I'm not requiring a specific form. But let's write out F in minus F out over AC. So what I wanted to do, the reason I wanted to leave some room here, I didn't actually end up leaving much room. I wanted to leave some room after the balance on A because I can use this result to simplify the A equation a little bit. So we know this. We know that dL dt is F in minus F out over AC. So what we can do over here to simplify things, again, it's not necessarily from the point of view of formulating an equation. Actually, first thing, let's just divide through by AC, just to keep CAL together. We're going to say this is F in CAN over AC minus F out over AC, CA. There's already a CA here. So this term can carry over, dropping the CA. So I'll just move this diagram a little bit. Okay, so this can be expanded using the product rule. So this is actually equal to CA dL dt plus L dCA dt. And we know that dL dt is F in minus F out over AC. So this is F in minus F out over A sub C. So notice that this F out, right, so if I multiply CA here, so this term would look like minus CA F out over AC, and we have a minus CA F out over AC here. So in fact, this, I'll use a different color. So this F out actually cancels with this whole term right here. And so we can simplify this equation by as follows. So we can collect terms a little bit. So we can divide through by L, and then move this Fn term to the other side, and this simplifies to dCA dt equals Fn over LAC times the quantity CA in minus CA minus K naught e to the minus EA over RT CA. So I don't know how necessary that was, but it did show us an example of using the product rule for differentiation to simplify an equation. So we now have an equation that purely has dCA dt on one side. That wasn't actually a requirement, but it looks a little cleaner. We now have a second equation with dL dt on one side. Now the question also asked to do a balance on B. So if we wanted to calculate CB as a function of time, that would look very similar to the balance on A. I'll get to it at the end of the video, but not everyone wants to watch the whole video. So if you do a balance on B instead of A, it would look very similar to this, except you would change all the subscript A's to subscript B's, and you would recognize that this reaction produces B, it generates B rather than consuming it. So the consumption term would actually be 0, and the generation term would actually be K times CA, or proportional to K times CA. So I'll do that at the end of the video for good measure, but when I start doing the balance on B, perhaps you can stop watching if you feel comfortable from what I showed on the balance on A. Okay, now the other thing that we would need to solve this, so remember I pointed out that this equation for CA depends on L that depends on time. So L depends on time, so I needed this other equation to formulate how L depends on time. But notice also temperature is a variable. And because we know we have a heat of reaction, and we know that K is temperature dependent, we know that this system cannot be fully understood without an energy balance. So we need to formulate how temperature can actually vary with time through an energy balance. Okay, so let's do it. Energy balance. And let me copy over the picture of our process. Okay, usual equation, accumulation equals input minus output plus generation minus consumption. Accumulation of energy follows, so energy in the tank is considered to be the internal energy of the fluid. So the volume of the fluid, LAC, the density times the heat capacity. That has to do with our specific choice for units on heat capacity. This heat capacity is on a mass basis. T minus T ref. Now that is some reference temperature, and it can be confusing because people often ask, what is the reference temperature? We don't actually have to choose it, but rather let's just say that whatever the reference temperature is that defines our relative energies, we don't want the assumption of constant density and heat capacity to be violated. So let's choose a reference temperature that's somewhere near where this fluid operates, and there are no phase transitions between any temperature of interest and the reference temperature. So accumulation is this quantity and how it changes from time t plus delta t to time t. So I need another term that is evaluated at t. The input energy is going to be the internal energy of the fluid entering the tank. So again, it's a very similar looking equation. The fluid flow rate in times rho Cp times T in minus T ref. Now I should put a delta T here, but actually what I'm going to do is I'm just going to put it in front of the bracket here so I don't have to write it for each term. And so now I need a heat of reaction, delta H reaction. So this is a generation term. I suppose I should actually write this is not what my notes write, but let me write the output first. So the output is going to be F out, rho Cp, T minus T ref. T would be the temperature in the tank, so it's the energy carried away by the fluid as it exits the tank. So this was the input term, this is the output term. Now energy, we're going to treat the delta H of reaction as a generation term. There is no consumption of energy because that's actually lumped into, or it's a irreversible reaction. So the delta H generates energy. Assuming it's exothermic, that would be a generation. If it's an endothermic reaction, it can be considered a consumption term, but in the end, the math works out the same. For a chemical reaction, a negative generation would be consumption. And so this would be minus delta H reaction. Times the rate of reaction, K naught e to the minus EA over RT, CA LAC. Okay, close the bracket. And so we do the usual collecting terms and defining a derivative. So let me I'm going to separate out these T ref terms. And usually in these problems, the reason we don't have to choose the reference temperature is because it actually falls out of the equation. That doesn't always happen, but it often happens. It does happen in this case, although it's not all that intuitive. It takes a few steps to show that Tref falls out. So let me just organize things in a way that will help me explain things. So LAC times T at T plus delta T. I'm going to factor out the rho Cp because it's constant and divide through minus LACT at time T minus LAC Tref at T plus delta T plus LAC Tref at T. And now this is going to equal F in T in. So I am, so what I'm doing, so remember we divided by rho Cp, that's why that's not there. And the Tref terms I'm going to collect separately. So this is going to be F in T in minus F in Tref minus this delta H term I'm going to divide through by rho Cp. Let's see. Okay, and minus F out T plus F out Tref. And all of this is going to be multiplied by delta T. Okay, so doing a little more factoring and collecting, I have AC times LT at T plus delta T. Remember, AC is also constant. It's a cross-sectional area of the tank, minus LT at time T. I'm going to divide through by delta T here. And I'm going to take the limit as delta T goes to 0. And what I have is I'm going to collect all the terms that have to do with Tref. LAC, Tref at T plus delta T. Minus LAC Tref at T divided by delta T plus F out Tref I'm going to make this a little smaller just to fit on the line. And then minus F in Tref and plus F in T in minus F out T. I don't like writing all this delta. Well, okay, I'll write it this time so I can rearrange it. Minus delta H Rxn K naught e to the minus EA over RT AC over rho CP LCA. Okay, now this is something that is hard to see, so I'm going to expand this out a little later in the video. stuff that I have circled in pink actually does equal 0. So in order to show that it equals 0, I have to actually go back to what the differential equation for dl dt looks like. So I'm going to just put that off. For the time being, I'm going to say this is 0. So I know that that's hard to see, certainly not obvious, but we'll come back to that. So I'm just going to finish up formulating the differential equation for temperature, and then I'll come back to explaining why that set of terms actually adds up to 0. So let's just drop it for the moment. Okay, so this comes out to dLt dt, and I'm going to divide through by AC. So this is going to be equal F in T in over AC minus F out T over AC, and then minus delta H reaction K naught e to the minus EA over RT. I hate writing out that term over rho CP times LCA. So yes, I divided by AC, which is why this goes away. Okay, and I can use the chain rule here. This is going to equal L dt dt plus T dL dt. And this, as we derived earlier from here, is going to be F in minus F out over AC. And what we will find is that this, when you multiply T, you'll have F out T over AC on the left side of the equation, and you have that on the right side of the equation as well. So these terms, so this F out, I know I'm not writing it out very clearly, but that F out term cancels. And so what we get is dt dt equals F in over LAC T in minus T, so I divided through by L. So now this next term, I'm just going to copy it. Since I divided through by L, I removed that. So now this is an equation for dL dt. So let me come back here, and I'm going to start. I'm going to just show the equations that we've derived. Okay, so one of them is this one. So I started off by saying it's likely that we will want to know the concentration of A as a function of time. And then I pointed out that L is changing with time, and so I can't solve this equation, even if we're not discussing the solution method, but regardless of the method, without knowing how L varies with time, we cannot really solve this equation. So that's why we did a balance here to get this second equation, dL dt, and then we also recognize that temperature is something that can change with time. So that's why this third equation was there. Now the order doesn't matter so much, but I will nevertheless copy this equation over here. And so if I was interested in knowing CA, L, and T, I believe this is a sufficient set of equations that could be solved to calculate those quantities. Now one thing, we're not done with this video. For one thing, I promised you that I would discuss why this is 0. And I haven't done that, so I'll do that next. But also, we haven't really been too specific about CB. Because it's an irreversible reaction, the concentration of B does not explicitly show up in the equation for the concentration of A. It also doesn't show up in the equations for L or temperature. So in principle, we could calculate Ca, L, and T without knowing Cb, but nevertheless, if we wanted to know Cb, we will have to do a balance on B. So first, I'm going to explain why these terms cancel, right? Then I'll do a balance on B, and like I said, the balance on B looks very similar to the balance on A. So you may not feel that it's necessary to watch the video all the way to the end. So let's come back to this equation. So let's come over here. I'm just going to copy these terms. And I feel like I owe you an explanation for why they're equal to 0. Just for clarity, I'm going to change the color of my text to pink. And I need to turn off notifications on my on my iPad. Okay, I'm going to rearrange things a tiny bit. I'm going to say L, by the way, this should be AC T ref, T plus delta T, minus LAC T ref at time T equals, or no, this is not an equation. No, sorry. What I'm going to do here is, oh yes, okay. I see what I'm doing in my notes now. Sorry, let's not do this. So what we want, so we have this term in the earlier equation, and I asserted that it's equal to 0. Okay, so now let me show you that it's equal to 0. So now this is from the balance on fluid. Earlier we showed that ACL at T plus delta T minus ACL at T. This is a balance on the fluid volume. We got this after dividing through by density. F in delta T minus F out delta T. Okay, so this actually, I'm not saying that this follows from this. I'm saying that this came from an earlier balance on fluid. So let's actually take a look at our earlier fluid balance. Okay, so this is this, right? LAC T plus delta T minus LAC at T is F in delta T minus F out delta T. Okay, so I'm going to manipulate this balance in order to show that this is equal to 0. Okay, so what I'm going to do is now multiply both sides by T ref. So I'm going to say ACL T ref T plus delta T minus ACL T ref at time T. equals F in T ref delta T minus F out T ref delta T. And let's divide through by delta T. So I'm going to just move delta T to 0, or to the other side. And so now notice that I have an equal sign in the middle. Let me just draw that a little more carefully. So if I move all the terms to the left side, then what I have here is this, and I'll have a plus F out T ref minus F in T ref equals 0. Now hopefully you will recognize this as being that term which I claimed was equal to 0, right? So now the two circles, I'm just reviewing, yes, they are the same thing. And so this is equal to 0 because that follows from the balance on the fluid. So even though that may not have been so easy to see at the time we were doing the energy balance, it is correct that I just dropped those terms because they add up to 0. Okay, so the last thing I promised you in this video was to do a balance on B. And again, this would be necessary if you wanted to calculate CB as a function of T. So I'll just switch colors, and we'll do that one last thing before ending the video. So this is accumulation equals input minus output plus generation minus consumption. And let's get the process diagram so that we can remember what these terms mean. Okay, so B is not consumed, it is produced. So consumption is 0. Generation is going to be generation by the chemical reaction. There is no B in the input stream, so it is not input to my system. And the accumulation is going to look like CBLAC at T plus delta T minus CBLAC at T, and that's equal to the output, so minus F out CB delta T. And this is a common mistake, or there is a common mistake when looking at the generation term. The kinetics of the reaction that produce B do not depend on CB. They depend on CA. So the rate of the reaction, or the rate of generation of B, is actually going to be K naught e to the minus EA over RT times CALAC delta T. Okay, so notice that the differential equation for CB as a function of T is going to depend on CA. And so earlier we said it was possible to calculate CA as a function of time without knowing CB as a function of time. That is true, but the opposite is not true. So I don't know if that's the opposite, but you cannot calculate CB as a function of time without knowing CA as a function of time. So the coupling between the CB differential equation exists. But even though the CA is not coupled, or the CA differential equation is not coupled to CB. So let's continue. I'm going to factor out AC. So AC times CBL at T plus delta T minus CBL at time t. I'm going to divide through by delta t. I'm going to take the limit as delta t goes to 0 in order to get a derivative. And this is going to equal minus f out cb, and then plus k naught e to the minus ea over rt, ca lac. And I think I forgot the ac, the subscript c, in the earlier line. Okay, and so this is equal to dcbl dt, which is equal to L dcb dt plus cb dl dt, and this is f in minus f out over a sub c, and so you can cancel some terms like we did with CA, and what you're going to get is L dCB dt equals minus f in over a sub c times CB minus how did I get a minus there? No, I don't think there's a minus. I think that's a plus. It's a generation term. Plus k naught e to the minus ea over rt. Looks like there was a negative sign error in my notes. E c a l. Oh wait, I have not divided by. Oh yeah, okay, no, that's fine. So I can divide through by L and put the L here and get rid of it there. So this should be, so right here, this should be a equation for CB as a function of time, which I could add to this system of equations. And then it would make it possible to calculate CB as a function of time. So I think we have accomplished our mission. Let me just quickly check. All right, I think we have.